Good morning, everybody. So I'm just going to take an opportunity to introduce myself first, and then I will pass it on to David to introduce himself. So my name is Erin Adams. I'm a professor in biochemistry, but my lab studies the immune system. So I think this might be topical in our discussion later on in our session 3, because I think there's a lot of related discussion about climate and vaccination that we can talk about, and how there's a lot of misinformation along those lines. I am also the Vice Provost for Research, so I now oversee a large component of the research at the University of Chicago. And so it's been a huge pleasure to get to know colleagues from across the research spectrum, try to support them in their research, and get them to hopefully talk to each other and collaborate. So it's great. Honored to be here today to talk with David, who I will pass it over to for his introduction.
So I'm David Keith. I'm a professor here in geosciences and the faculty director of this climate systems engineering initiative. I've worked on climate since starting in the late 80s and full-time since about 92. And I worked on a big variety of things from sort of atmospheric science, including experiment, to energy technology policy, a lot of work on energy system decarbonization and on these climate engineering technologies, both carbon removal and solar geoengineering. Kind of wandering back and forth between public policy and sort of technology assessment and climate science.
Thanks, David. And I think, probably our first topic to touch on would be how you really define climate systems engineering, and maybe give some examples of what you mean by that.
Sure. So that's a UChicago term. UChicago hired me in here under that term, and to me it means some overlap of climate or Earth systems science and the kind of older concepts of systems engineering, meaning kind of thinking systematically about means and ends and uncertainty and so on. And the topics that we include inside it are solar geoengineering or sunlight reflection methods, or whatever you want to call them. Basically, this set of ideas for how humans might deliberately make the Earth more reflective to reduce some of the risks of accumulated greenhouse gases. And then the second big piece of it is open systems carbon removal, meaning different ways that we could, humans could permanently remove carbon that we put into the atmosphere from burning fossil fuels, in ways that are kind of using the Earth system by, say, grinding up basaltic rocks and putting them in soils or in the ocean or what have you. And that the other piece are some things we might do to reduce the melting or the loss of mass from the big glaciers, which have these global implications for sea level.
So obviously, I think one of the issues that a lot of people are concerned about, but also really interested, is the environmental impact. And I mean that both positive and negative. I think impact is usually considered to be a negative term, but we've talked about, Tiffany showed beautifully where we are going, and if we don't do something, whether it be reducing carbon dioxide emissions or trying to pull carbon dioxide out of the air, or some of the approaches that you just touched upon, we know where we're going. So what would you say would be some of the impacts and benefits, I'll throw in, of climate systems engineering?
So I think there's nothing meaningful to say about climate systems engineering as a thing. I think it's more useful to, at least the way I think about it, is we need to think about the climate problem in 4 dimensions. So decarbonizing the economy, basically transitioning our economy so it doesn't emit carbon dioxide, is the #1 thing to do. And that breaks the link between economic activity and carbon emissions. And then carbon removal can break the link between essentially historical the historical buildup of emissions and concentrations. It's concentrations, the amount of CO2 that's actually mixed in the air that the climate feels at any time. And maybe the most important sort of single thing to say that was on Tiffany's last plot about climate science is that climate change is proportional to cumulative emissions, which means even when we bring emissions to zero, we haven't stopped the climate problem, we've just stopped it getting worse. So the power of carbon removal is it's the only way we could go backwards, the only way humans could reduce the long-run climate risk. And then solar geoengineering can't break, but it can weaken the link between the amount of the concentrations, the amount of carbon dioxide and other greenhouse gases in the atmosphere, and the amount of climate change, and then local adaptation, ways that we can reduce the impacts on ecosystems or on human systems by some kind of local changes to infrastructure or behavior. These things reduce the felt harm of climate change for a given amount of climate change. So those are, I think, the 4 high-level things that humans can do to manage the climate problem. I don't think there are any others, and I don't think it makes sense to lump those together. You might say I'm running a thing on climate engineering. That's true, and I think it's useful in research terms to do it, but they're deeply different, solar geoengineering, carbon removal, different in the time scale in which they act, different in the politics, different in the physics, different in the kind of the distribution of risks and benefits. So for carbon removal, any carbon removal activity will have some environmental harms and costs where you do it, but if you remove the carbon, there's a kind of perfect global benefit, and that benefit is globally distributed, whereas the harms are at the place you do it. Solar geoengineering is quite different in the sense that many of the large-scale ideas, like putting aerosols in the stratosphere, would have both global benefits and global harms, but really almost no local effect at all, because the thing that does it is quite small. So they're really deeply different things. So I think there's nothing I know that I can say much about in general climate engineering. What I can say is that I think there really are 4 dimensions to the problem, and I think we need to take them seriously. We may decide not to use some of them or to use them, but I think that is the climate problem we have. Those are the knobs we have.
I think Tiffany showed beautifully our ability to predict where we are going on a large scale. She also really pointed out where there are big knowledge gaps in the climate systems engineering research area. How do you feel the predictions are, and what are the major knowledge gaps? Are they related to what Tiffany
So again,
talked about,
I don't have nothing that I know how to say about climate systems engineering generally, except that it would be good to do more research, and that's why we have this program. I think they're so different for the different cases that unless you talk about kind of specific things, at least talk about solar geoengineering separately from carbon removal, it's not clear what to say.
So let's talk about your, the one that you feel most comfortable talking about.
I'm comfortable talking about either. I mean, I think maybe this is a challenge that we were talking about before. I'm just deciding. They're both important. I work on both of them. Totally happy to talk about either one, but they're just really quite different. Yeah, I mean, I might give you 2 examples. I think it's the long-term way that the Earth system will deal with or remove the carbon that we put into it we basically moved carbon from the geosphere from underground by burning coal and gas and oil. That puts carbon in the atmosphere, and then from the atmosphere it moves into the ocean and into the surface biosphere, but it can move back and forth between those reservoirs. If you want to do something that really undoes what humans did, you need to take carbon back into some stable reservoir where it's sort of permanently removed. And one of the ways to do that is by weathering rocks. Carbonic acid, it's called. Carbon dioxide, when it mixes in water, forms an acid. It's a weak acid. But you probably all know from kind of high school chemistry, bases and acids mix together to form salts, and that's what happens in the ocean. So in the long run, that carbonic acid wants to weather some basic materials on the Earth's surface, and that will then make stable salts. So, for example, you could grind up basalt, a kind of rock that is basic, and put it in soils, and that will, I think it's for certain that it will have some effect in permanently removing carbon dioxide. There's no doubt that there's a reaction between these basalts and carbon dioxide that permanently removes it. So that's a great thing. But there's an enormous uncertainty about the extent to which actually doing this in soils, which is now being done commercially, whether it actually is accelerating the weathering very much, what the environmental consequences are, because some of these rocks have, for example, olivine has chromium in it, and chromium is a quite toxic metal. So there's deep questions about whether or not this, the environmental consequences of doing this would be in agricultural soils. So that's an example where there's, I think, very high uncertainty and a high level of overhype, and yet there's an underlying thing there that makes some sense. For one particular kind of solar geoengineering, which is putting sulfuric acid droplets in the stratosphere, I think that if we're talking about doing that in a way that's relatively limited in scale and balanced between the hemispheres, I think the answer is there's actually very high confidence in predicting what will happen, because there's this enormous body of science in studying the impacts of aerosols in the atmosphere. So the first good quality papers that looked at stratospheric sulfates were in 1960. And there's been this immense amount of knowledge focused on understanding sulfate aerosols because humans emit them as pollution. And so because of that, there's actually, we can make, I think, quite confident predictions about what might happen.
Great. Another key aspect of this discussion, of course, is how do we educate people about this approach, approaches, I should say. I think I remember decades ago there were a series of apocalyptic movies about major weather changes and how that impacted society, very Hollywood-esque. And so I wonder how we can get out information about what this means, in our discussion today, and educate people about the benefits and the risks of this.
Having conversations like this, having people who are science communicators be embedded in these research efforts to try and explain this in language that makes sense, having conversations that is kind of transparent about risks and benefits. I think one important thing to say that sort of hints at in the earlier questions were, what's the role of commercial actors? So, for example, for solar geoengineering, I think that the right role for commercial actors is that there shouldn't be any. That I think this is a thing where they're really all the questions are really not about reducing costs, since the costs of doing it are already seem to be cheap. It's really about increasing our confidence in what would happen, being able to predict it, being able to control it, having kind of a sense of democratic control over what happens. So I think there's really not, I think there's good reasons to want to exclude private actors. Whereas for carbon removal, and I did found a carbon removal company, I'm not involved in it anymore, but I think there's carbon removal technologies look a lot more like regular energy system technologies. They require big amounts of capital, and I think there is an appropriate role for private industry responding to government incentives and controls.
Are there resources out there that you could point the members of our audience to educate themselves better on this?
Sure. I mean, there's a set of books and TV programs and papers, and we've got a website that's got some of it on. Yeah, there's a fair amount. The Wikipedia entries are not terrible now. Yeah,
that's great. You got all the Wikipedia.
It's amazing. It's a triumph of human collaboration.
It truly is.
It shows you that if you set the rules right, people can collaborate very effectively, and with fundamentally the same media as social media, where if you set the rules to the other ways, you can get other outcomes.
You touched upon, I think, the next topic that I'm really interested in discussing, which is you can have the technology to, mediate how much sunlight comes in and hits the planet, but putting that into the atmosphere is not just going to affect a square mile. It'll affect the entire planet. And so, you know, what are the current discussions on about how this, you know, the legal aspects of this, both domestically and internationally? How do we move forward as a planet in discussing this?
Happy, maybe we'll just talk about, maybe to sort of narrow, but for a while I'll talk about stratospheric aerosol or sulfate aerosol solar geoengineering, because that's the thing that maybe is most visible, where there's fast-moving talk about it. And I'm happy to answer that question, and I'll answer a little bit now, but maybe let's circle back and say a little bit about what we know. Sure. But the answer to that question is, there is lots of talk. I was privileged to be an advisor to something called the Global Overshoot Commission that ran over a few years, and we had meetings around the world, and there were 4 ex-heads of government on that. So Philippe Calderon, Kim Campbell of Canada, a couple others, and a bunch of everybody, all the commissioners were, you know, had served near the top of some global government or some national government. And I think the answer is those conversations are beginning in a serious way. And the big environmental groups are also getting involved in a serious way. So Environmental Defense now has a serious program to raise money for research on solar geoengineering and to advocate for research and for governance. So there's ways in which these are changing very quickly, but there isn't any global structure for, you know, there's no treaty that provides a clear answer for how humans make decisions about it. I would say that maybe I'll give a little background. I mean, I think my view on this topic has changed quite a bit. So I was involved early on in around late 80s. And in 1998, myself and Ken Caldera were at a meeting where somebody who was a big proponent of solar geoengineering was basically saying that it was just a cheap fix and it would work really well and we should just do it. And Ken and I stood up at the back of the audience and said that this person was wrong, and that while there was no question you could reduce global average temperatures, it would inevitably be very unequal, so you'd make some areas worse off. And to Ken's huge credit, he went back to his lab to try and prove that it would be very unequal, and did the first climate model experiment along with Bala Ohasimdi, and that experiment actually showed that the result was pretty equal. So it's now been more than a quarter of a century since then, and there's been essentially every major climate model has been used to explore how solar geoengineering might work. And I think it's fair to say that in a healthy way, very healthy way, the climate science and environmental science community has been biased to look for problems and to show how this wouldn't work. But after a quarter of a century, I think that what we've found is really quite surprising, and it's changed my view about this a lot, in the sense that I used to give talks where I'd say, it's very uncertain and it's risky, but we should at least look at it. And my view now is that limited, and we have to define what I mean by that, but limited and hemispherically balanced sulfate aerosol solar geoengineering, that in fact there's very strong evidence that it would have large benefits, and that the benefits would be quantitatively large compared to the harms, the side effects. And I think we really know a lot about it now. Not that we know everything, but we know a surprising amount, because it's been done in all these climate models, and because, while in some sense it seems like a new thing, it's not really a new technology. It's just applying something that we already know about, the way aerosols affect the atmosphere, applying them in a new way. And so for that reason, I think there's this sort of disconnect where there are very strong views, like one of the earlier questioners said that some environmental activists think it's a false solution, which absolutely is true, although it's not clear that false solution means anything other than a solution I don't like. I mean, that's not, false solution isn't a statement. You need to give a reason why you think that's true. But I think the evidence that it can be useful is quite strong. So to give it a sense, in a paper that we just published, but there's tons of these papers, and the big point is there's no papers that contradict what I'm saying. That is, there's no paper that I know about where in a climate model you have pretty hemispherically balanced and moderate stratospheric aerosol geoengineering where you don't show this effect, where you have very big benefits of reducing climate changes pretty evenly around the world. And when we start to look at side effects, they seem quite small. So for example, sulfate aerosol air pollution is the most important environmental global killer that we have, period. So it kills now something of order 5 million people a year. And in very polluted cities, it shortens people's lives by several years. And in a way, the good thing about sulfur aerosols is that the devil we know. We've worried about their air pollution for more than a millennium. The first law that I'm aware of was a promulgation by the king in London banning the burning of sea coals, high sulfur coals, in 900. And the first attempt to put a scrubber on a coal-fired power plant was the Bankside plant in London in the 1890s or 80s, I can't remember. And so there's this enormous history of dealing with the environmental impacts of sulfur, which means we know a huge amount about it in quantitative detail about what its harms are. And that means that we can say quite accurately that if you put 1 million tons a year of sulfur in the stratosphere, which sounds like a giant number, it is in some ways, but for context, humans were putting almost 100 million tons a year into the lower atmosphere in the peak in the 1970s. And if we do that, we can actually calculate pretty accurately what the air pollution effects are. So doing that, and that's one of the first things you want to do, would lead to excess deaths, excess mortality of something like 10,000 people a year, which is pretty horrifying. But the reduction in deaths from heat, from the cooling you'd get, would be something like 500,000 a year. So the ratio of benefits to harms is sort of between 10 and 100 to 1 in that, for those particular benefits and harms. So that's kind of, to me, one of the examples why I and many other people, including lots of people in the environmental community, now take these ideas pretty seriously, which isn't to say that there's a right answer about whether we should do it or not. That's a policy judgment where there's no, I can't as a scientist tell you what is the right answer.
So I had a lot of questions buzzing around in my mind. So how reversible is this technology? So say, this is put into the atmosphere and we decide it's not working well.
Sulfates last in the atmosphere for about 2 years if you put them in the stratosphere. And maybe it's important to say that if you gave me the choice of banning this forever or doing it at large scale instantly, kind of pushing a button and suddenly doing it at enough to cool the Earth by 0.5 degree C or a degree C, I would choose to ban it forever. I think that'd be crazy to do that. But that's not realistically the choice we face. I think the only view that I think most other people working on this think makes sense would be to start it in a small subscale way and then monitor carefully, and then one gets to make decisions, whoever's making decisions, to scale up or down. So it's a thing that naturally is pretty scalable and naturally only lasts for this kind of year or two time scale.
That's great. And we've spoken a lot about the impact on humans, but of course, we are not alone on this planet. There are, ecosystems that, are now being thrown out of balance because of climate change. What are the estimated impacts of this technology, particularly the aerosol technology, on? We talked a little bit about the soil mediation, but I'm sure that this has been a topic of discussion. So maybe you could share some of the environmental impacts.
Yeah, I think it's hard. So, the main environmental impact is that by reducing climate change, you reduce the environmental impacts of climate change. Yeah. That's the fundamental goal. And it's hard to find much quantitatively beyond that. So I think in general, most environmental impacts depend on the climate change. So if you've reduced quantitative climate change, then you've reduced the environmental impacts. I think the question is, what ways are environmental impacts increased, or what ways does that not work? And so one obvious thing is you think you're going to make less sunlight, so maybe that will be a problem. But it's sort of only 1% less sunlight, and there's lots of other things that vary sunlight at that level, changes in cloudiness and surface aerosols. So I think there would be some effect. All I know about where people have done carbon cycle models show that solar geoengineering tends to increase net primary productivity, but not in every place all the time. Mm-hmm. There would certainly be, there's environmental impacts of sulfur deposition. That's an obvious question, acid rain, but it turns out to be very small because it's pretty even and it's just quantitatively so small. And again, that's something we know about really well. I think the big question is what are the unknown unknowns? What are we forgetting about that could be some surprising ecosystem impact? I think it's certain there would be some. I think one thing you can say for sure is if humans ever did this, there would be some surprising and bad outcomes. I think that's kind of always true with any intervention like this.
Yeah, great. So the final topic that I wanted to raise, and then we can talk about some of the questions that we received over email and then open it up to questions from the audience, is really the ethical aspect. And you've touched upon this kind of throughout, but what do we need to think about if we're considering an implementation at an international level or at a local level?
Lots. I think one way to separate out is I think there's issues of distributive justice and procedural justice. So where the procedural justice is who gets a chance to be part of making the decisions on these topics. And obviously we don't live in some magic world of global democracy. And I think in practice for solar geoengineering, the decisions would get made by some coalition of countries. We talk about what that might look like. So it's not going to be very procedurally just, but you could imagine ways that were better and worse. I'm personally very interested in ideas for kind of what are kind of citizens' assemblies or other ideas for kind of consultative democracies for people to get a sense of what regular people think, not what academic experts think or people from different interest groups. And then there's the distributive justice question of however the decision was made, who actually benefits and who's harmed. And I think that's or somehow it feels different for solar geoengineering in some weird way than it does for climate. So let me say the most basic injustice for climate. So is probably most of you know, I mean, most of the emissions have come from the rich world's CO2 emissions. The harms of warming, we now know from work, especially quantitative work by people like Michael Greenstone, are the harms are felt most, the harm of additional warming is felt most in hot countries by people who are poor and by people who are old. And I'm not just saying that. These are things we know really quite quantitatively and specifically. And as it warms up a little bit, there's actually benefits. So mortality goes down in cold countries. So in any city or any place, for example, if you look at death rates versus temperature, you'll see a U-shaped curve where when it's hot, death rates go up, and when it's cold, death rates go up. And so it may be not surprising that if you warm the world, you see harms, and really quite huge harms, in the poor, hot parts of the world. And you see some benefits in the cold parts of the world. That's of warming. So to the extent that climate engineering reverses it, it'll have the reversed impact. So climate engineering, and a bunch of specific studies show this, I should say climate engineering, even stratospheric solar geoengineering, would have the biggest benefits for people in the global south, for relatively poor people in hot countries, and might even have some disbenefits, some harms for people in colder countries. And I think that's kind of a core to some of the ethical challenges around its use.
So I wanted to touch on some of the questions that we received. I think you've actually answered a lot of them in just what you've said already. But maybe, and I think we're going to talk about this more in our third session. One of the questions centered on publicly available data and how when that isn't public, and we touched upon that, I think when Tiffany was answering some questions, when those data are being collected by private industry, or when they are taken down from publicly available websites. How does that, I mean, and Tiffany can maybe chime in as well, but how does that impact our ability to predict and analyze effects based on this?
So for solar geoengineering, I think almost all of this is done by open science in an open scientific way. And so, while not every piece of data is on a website, actually journals have got much better in the last years at forcing you to give your data as part of a journal publication. So I'd say in general, because this is really just building on existing atmospheric science, it's pretty open. Somebody mentioned that there is this company, so-called company called Make Sunsets. I regard that more as a kind of theater stunt than a company. They're not transparent. They're also not really doing anything in a sense. That is, they've released less CO2, I think. They released less sulfur, I think, in all their operations than a single flight to Europe releases. So they're not, in a sense, really doing anything. It's just a stunt. But they're not releasing data from their stunt. because there isn't any data. There's an Israeli company called Stardust that I think is significantly more serious. I don't know what they're doing. It's secret, but I also don't think it matters that much or they're really doing that much. That's my judgment, but we don't know, and I'd rather they didn't exist. No, to be clear, I've talked to people. I've told them that. They kind of half agree with it, but whatever. They are. That's what they are. But I also don't think it's that big. This is fundamentally mostly done by open science. I think it's very different for carbon removal. And I think it's very different for the different kinds of carbon removal. What is the appropriate level of open or closed science? So I think for things where you can measure the inputs and outputs easily, I think it's very reasonable to have private industry have secrets inside. So I think, one of the places I'm pretty happy with capitalism working well is, for making solar panels, people are very secretive about exactly how they make them. Yeah. Because what matters is that outside users can measure objectively, easily, how well they work. And hopefully outside regulators can say what are like the metal contaminations coming from the factory. But you don't need to see everything inside. You need to know the inputs and the outputs. And so I mentioned that I founded this direct air capture company. I'm not involved anymore, but I think direct air capture is a bit like solar in that sense, is that whether it's a good idea or a bad idea is going to be set by public markets in the end and by regulators. But you don't have to be open about what's going on inside because it's really easy to measure exactly how much CO2 has been removed and what the inputs and outputs are. And in the end, that'll be done by regulators. But for, say, putting alkalinity into the ocean, which I think might be one of the most important scalable, low environmental impact ways to remove carbon, but I said might, but I think it's really one of the most important potential ways to remove carbon. That's something where I think it really must be done in a public way for lots of reasons, including the fact that the global oceans are not owned by any country outside the exclusive economic zones. But also because of sort of issues of deep uncertainty in an open system. But presumably, if it does happen, it'll be a mix where you could imagine companies competing for contracts to put a certain amount of alkalinity in a certain place to a specification, but I hope governments or NGOs deciding what's done. But I think the point is it's very different in the different cases. What's the appropriate level of open data?
Yeah. You mentioned regulations. Are there any current regulations against modifying the environment in this way?
Well, I mean, that's what this way means. In general, no. In general, regulations are, it's really complicated. You have an hour? So in general, regulations get written around specific activities that cause environmental problem. And, I'm child of environmental regulators, and I think that regulations are usually written too slow and they should be stronger and so on. But general, the regulations are written when we have a problem to govern some category of sources. And in general, but there's some exceptions, we don't have kind of generic regulations that say don't damage the environment. There are some important exceptions. So the US has NEPA, the National Environmental Assessment Act, which binds anything that has federal money or federal action under some broad claim of environmental harm. And then there's this process you probably heard of, environmental assessments and so on. So that's a quite broad one, which allows third parties to bring suits for anything that the federal government is doing. And some other countries have similar versions of that. If you think about, say, climate change treaty under the Framework Convention, which is the international convention, or the ozone protocol, those in the end regulate specific categories of sources. There's not a general treaty prohibiting changing the climate. There's treaties and rules now that in some countries put prices on or prohibit different kinds of emissions. So for I think you're sort of hinting at for stratospheric sulfates, the answer is, as a pure legal matter, there is not a legal restriction to somebody flying an airplane and putting a giant amount of sulfur in the stratosphere. There is an underlying principle of international law that says that states shall not cause significant transboundary harm to other states. And that's not a trivial thing. And indeed, the most important case that defined a lot of how that works involved sulfur and Canada and the United States. I'm a Canadian where I have both citizenships, but Canada had a nickel mine in Inco that was the biggest source of sulfur pollution in all of North America, and the U.S. sued Canada under that provision of international law, and some of the result of that suit is one of the definitions of this significant transboundary harm. So that's the only thing we have. There's not a general rule. And so that maybe I'll just finish that. It's not very complicated, but it gives you a sense. So if right now in the US, I forget the exact rule, but there are good regulations on the amount of sulfur that can be in aviation kerosene. So if I'm flying a commercial aircraft, there's a limit to how much sulfur can be that. But if I separately fly an aircraft and just have a big tank of sulfur and release it, it's not bound by that regulation.
So there's not a food and drug, an FDA equivalent for these types of engineerings?
No, and I don't.
There would be an assessment about.
Well, I think there will be. I mean, there have been a whole bunch. To be clear, there's been lots of open assessments. There's been National Academy reports, and there's a great report from the UNEP called the One Atmosphere Report. That's sort of the best kind of international report maybe on this topic. So there's lots, but there isn't some global environmental regulatory entity with power. I think in some ways there should be. We have a planetary problem and we need planetary institutions to deal with it at some level.
Great. Let's see. I mean, most of the other questions we've already touched upon. Maybe, I don't know how we are on time, but maybe we could open it up to questions from the audience.
Yeah, maybe I'll say something very quick. I sort of open by saying there's these 4 different things to do. And at least for decarbonization, carbon removal, and solar geomass sharing, I can say at least how I think about how those should interact over time. So my view, and you may be surprised because I've worked on carbon removal and even formed this company, is I think that it doesn't make sense to put significant effort into removing carbon until emissions are down a long way towards zero. Basically, I think if you ask me as a citizen to vote on how to divide our effort between decarbonizing the economy and carbon removal over the next few decades, I would say put at least 95 or maybe 98% of the effort into decarbonizing and only a couple percent into carbon removal. I think right now the goal for carbon removal should simply be to understand better what the costs and environmental consequences of the different technologies are, which I think does mean actually some level of commercial deployments. You can do it at a scale to understand, but still tiny. And that's my opinion, but it's also kind of what's happening. So we're now spending $1.7 trillion a year in clean energy, which is stunning. And while we've heard this gloom, the happy news is that we are probably at peak emissions now. Emissions will probably come down from now, which is an amazingly successful fact.
We hope.
And we're only spending, so 1,700 billion on clean energy. We're spending maybe 10 billion on these carbon removal technologies or less globally of different kinds. So that is kind of the ratio. And on solar geomass sharing, I think my view is that people need to debate it and take it more seriously because there's evidence that it could really reduce risks for people now living, especially people now living in hot countries, and for ecosystems that I and many of us care about a lot. I think that evidence is strong, and that's why it's worth thinking hard about it.
But the latter point, you think that that's something that could be considered now instead of waiting for the decarbonization efforts to take effect? Or do you think that
I don't know why. I don't know what the argument for waiting. There may be. I think there are good arguments for never doing solar geomass sharing, but it's not clear to me why you would wait.
Okay.
It feels to me like if you're ever going to do it, the time to start is basically now, so you can start slow and so you can get the benefits centered at peak concentrations.
Okay, great. All right. Well, maybe we'll open it up to the audience for questions. There's a microphone coming.
Hi, I'm a Harris MPP student, and so you told that solar geoengineering talk started in the 60s, and we also know that there is a growing scientific evidence that geoengineering could pass cost-benefit analysis. But as far as I know, it remains purely theoretical and with no real-world experiments except the natural case of volcano eruption in 1991. What are the main obstacles preventing an experiment today, and how do you think is possible to overcome them? Do we also need a planetary institution for this? Thank you.
That's a great and natural question. And so first of all, I want to really push back strongly on the idea that it's all theoretical. The basis of the claims I'm making about solar geoengineering are based on this giant body of climate science that, as Tiffany said, goes back for a century, well, for centuries. So the point is, it's easy to say they're just based on models, but the models are not things that some coder cooked up in the basement. The models are built on these detailed observations of the atmosphere over a very long time, and going back to Tyndall and enormous amounts of work. There are probably thousands or tens of thousands of scientific papers dealing with the effect of atmospheric aerosols on temperature and an enormous number of measurements. So I think it's really important to say that that there is this huge empirical body of practical knowledge that supports the claims we're making about solar geoengineering. And I'm a scientist. I'd love to see more experiments, but experiments are not likely to change our knowledge significantly because there's such a depth of prior experimentation. And I think there's been a great confusion about what these experiments are. So somebody in a question to Tiffany said that, I forget the exact thing, and the person can speak for themselves, but they said something like there's people advocating doing it and they were shut down. So I think they were talking about, say, the experiment we were doing at Harvard, but that experiment was truly a scientific experiment. It would have done something very nerdy and measured some like particle coagulation coefficients. It would not have been a test about whether solar geoengineering worked or didn't. There is no such test. And I think the only thing that one would do is you could add to scientific knowledge, and then in the end you can start this kind of subscale deployment and monitor. But I think the idea that there's some yes-no test is the right question if you're thinking of some encapsulated technology, but it's not really the right question for a thing like this.
Two questions. Dave Schultz. I had worked at EPA for 40 years and been retired 10 years, but before I retired, I visited a CO2 capture system at a power plant, which, while it only was a demonstration taking 1% of the plant's capacity, the cost was almost equivalent to the SO2 and NOx acid gas capture systems for the entire 100%, the flue gas. And from their own studies indicated that to get rid of the CO2, they would have to do an underground pipeline at least 800 miles for a geologically stable location. So it didn't seem either practical or economic in terms of proceeding with CO2 capture. So the first question is, has the technology advanced to a point where you think that this is really a viable technology to consider, full scale on a number of plants?
So just for context, I think what you're asking about is capturing carbon dioxide from point sources and injecting it underground as a way to manage the emissions from those point sources. And so, yeah, I think at this point, it's not my opinion. It's clear that it's a viable thing. There's about 40 million tons a year now of projects globally, quite a lot of projects, and new projects are coming online. And the typical costs are hard to know, but I think thinking of order $100 a ton CO2 equivalent is the right kind of number, but they vary a lot in the kinds of projects. I think the way that we think about that is part of the energy system has really changed with the stunning advent of really cheap renewables. So when I worked on CCS regulation and technologies in the late 90s or early 2000s, we were thinking of coal-fired power plants. But I think it's obvious, nowadays the right answer is coal-fired power plants are just going to get removed, taken over by solar or gas mixtures. I think the places where CO2 capture and storage like that probably makes most sense are, most obvious one is cement plants, where the emissions are inherent in the cement. They're not just from the fuel, as you know, and it's about 4% of global emissions. So I think that's probably the single most important target. And then also some other big industrial ones like ammonia and steel making are ones that people think about. And then I think the question of whether or not it's relevant for electric power is unclear. It depends on how the dynamics of electric power systems, how, for just cost of kilowatt hours, solar is just, it's the most amazing thing. It's fantastic. Solar just wins. But of course, solar doesn't work at nighttime. So that's a saw off against batteries versus natural gas, or natural gas with capture, where we don't really know where the cost of natural gas with capture will going to land.
Thanks. Second question. I share your concern about if we proceeded to proceed slowly and carefully. And so if proceeded with systems for stratospheric sulfate aerosol injection, is it technically feasible to be able to evaluate that in terms of injection within a fairly limited area?
I think you got to figure out what you're evaluating. This comes back to the prior question that the lady to your right asked, and I think it's really hard to get at. So what are we asking? If you're asking, do aerosols in the stratosphere scatter sunlight? The answer is yes, from physics that's about as certain as Newton's law. Even the strongest critics, people who say that I should never be allowed to say what I'm saying and I shouldn't be employed in this university, would agree that if you put aerosols in the stratosphere, they scatter sunlight. And they'd all agree that if you scatter sunlight, it cools. So the questions are really more detailed questions about what is the size distribution of the aerosols, what is their effect on ozone chemistry, what is their effect on the upper troposphere, a bunch of really pretty specific questions. And for each of those questions, you need a different kind of experiment with a different scale. So I think what you're harkening back to is this idea that somehow we could just test it and find out in a kind of binary way if it works. And I think in a deep way, that's not the way it is. Actually, I want to come back to one thing on your previous question. You said that I think it's clear that most people, especially people on the environmental left, don't like CO2 capture and storage. It's not, to me, completely obvious why that's true, but it's a fact. And people will often say it's very expensive, but I want to encourage you, especially those of you who find yourself in that point of view, to ask yourself, expensive compared to what? You got to make a comparison. So, for example, my long-term home is in Canmore, Alberta. We built a new house that we're very proud has no gas line. It's all geothermal and super insulated, and we have the amazing German windows that are half a watt per square meter per degree K. And I know, because I'm a nerdy person, I actually calculated what the dollars a ton CO2 avoided was of us buying those fancy windows, and it was over $1,000 a ton CO2. And the reality is there's a giant cement plant near our house that has about 2 million tons a year of CO2 going into the atmosphere, and you could capture that for about $100 a ton CO2. And so you got to figure out what you think is expensive and not.
Thank you very much. The United States, well, in fact, the world is going through an industrial renaissance with AI, and we're seeing a lot more future need for energy, and as we build out these data centers. And I know that they're looking for sources of clean fuel, but I'm just curious, to what extent would this contribute to building up CO2 emissions, and how we're trying to get ahead of managing that?
Well, nobody knows. It's very fast moving. I think what you're saying is definitely something that many other people are saying. I think if I'm a betting person, I would bet that it won't end up being that important, but obviously I might be wrong. None of us knows. Even in the last, so far this year, we've had revolutionary changes in the amount of energy needed to train these models. And my view is there's a level, I'm not an AI expert, but my view is there was a level of overhype in some of the big American AI companies that assumed that just scaling was the way to go. And there's also pretty rapid changes in chip development that are beyond the kind of NVIDIA chip. So I'd personally be surprised if we end up using a significant fraction of primary energy on computation, but I might be totally wrong. I don't have much confidence. It's just like I'm giving you my guess. Right now, to be clear, in terms of contributing to global primary energy, it's pretty small. It's like 1% and a bit of electricity, which is sort of less than 1% of global primary. Maybe it'll end up being really big, but my guess is that transportation and materials and agriculture and so on will be the main energy use, not computation. But who knows?
Hi. Can you talk a little bit more about the unintended consequences of solar geoengineering and the sulfates, aerosols?
Sure. So let me think. Some of the ones that I've wondered the most about and worked on are if you're going to put sulfate aerosols in the stratosphere, they're going to filter down. They all come down. Anything you put up will come down. So what is the effect in the upper troposphere, the upper part of the turning over atmosphere that we live in? And that's, especially in the tropics, very clean. So the amount of additional aerosols might be significant, and there's a bunch of ways it might change the way that aerosols form naturally in ways that might have significant climate impact. So there's a bunch of questions there that I think we don't understand very well. There's questions about the stratospheric circulation that we don't understand as well as we want to. There's questions about what the stratospheric heating from these things does to the stratospheric circulation. There's still questions about atmospheric chemistry, especially given the fact that most of the models just assume that all the sulfate is in sulfate form, but now we know empirically that actually a lot of the aerosol in the stratosphere is organics. There's questions about the impacts of the diffuse light. You make slightly more diffuse light. Does that impact ecosystems? In what way? There's questions about whether, in general, it reduces climate change in most places, but in what, more specifically, in what ways might it exacerbate climate change? What are the areas that it would do that the most? There's a giant list of questions that those of us working on it have that need answering.
One question from me. We might have time for one more before we move on. David, you stressed a lot in your talk that if we did do sulfate injection, it would have to be hemispherically balanced. What does that mean or look like in practice? And what might be the barriers or the problems with achieving that?
So all it means is, for very small amounts, it wouldn't make much difference. But if you're going to cool one hemisphere by, say, half a degree and not cool the other hemisphere, then you move, there's a band of moist. Anybody who's looked at a global map will see more or less that there's kind of a green band near the equator, and then there's dry brown bands on each side, sort of centered at 20 degrees. That's the most basic feature of what we call the general circulation of the atmosphere. The Earth air rises on average right near the equator. It shifts with the seasons, and that makes heavy rain. And we know for sure that if you do the cooling in just one hemisphere, it kind of pulls that zone towards that hemisphere, and that would have benefits and disbenefits that were strong, and it would be uneven. And so one of the kind of, I think, robust findings is if you want to, which may not be what people want, people disagree and have different interests, but if you're a global utilitarian and you want to just reduce climate change without making it exacerbating anywhere, then you'd rather have it balanced. And technically, balancing it is easy, and there's feedback controls that people have thought about, and you could do this just from 2 or 3 or 4 airfields, and some in the northern and southern hemisphere. I think the bigger question is it politically hard to balance? So some critics of this imply that that requires some very complicated political agreement. I'm not sure it does. I think you really got to start thinking through what are the actual incentives that different states would face.
Thank you.
I just want to ask something that came up to me as we were discussing that, one of the most, in my limited knowledge of this area, the most effective ways of carbon capture is photosynthesis. And we haven't really talked about the effect of deforestation or reforestation and whether that is a viable approach as well.
So here's a pretty shocking fact. Ask yourself, of the total change in carbon in the atmosphere since 1850, what fraction of that change is due to everything that's happened in the biosphere? That is, the fact that we had massive clear cutting and regrowth and all these biospheric changes and all this human impact on land, compared to fossil fuels plus cement. And think what the answer is. So think what fraction of the total change of CO2 in the atmosphere is due to everything about the biosphere compared to fossil fuels plus cement since 1850. Just think of the answer. I'll tell you. The answer is it's about it's a couple percent. So basically, it's dominated completely by fossil fuels plus cement. So it's true that there's some places where, for example, in Eastern North America, including here, where when we, this is more true when I used to teach in the East, but, we humans cut and clear cut big chunks of hardwood forest in New England for agriculture, and that had huge emissions. But then the emissions, of course, reversed as it's all regrown. Plus, you've got the effect that we're fertilizing the atmosphere, so carbon dioxide and nitrogen tend to enhance plant growth, and so we actually have additional uptake. And all those things have ended up roughly canceling out. I think the important thing, I keep coming back to the fact, I think there's lots of really good reasons to care about protecting natural environments because we care about them and we want natural environments. But I think that they're mostly not the issue for carbon. I think it's important to keep policy simple. And the climate problem is primarily driven by moving fossil fuels from the geosphere, from deep underground, to the active biosphere. And if you want to deal with the climate problem, you need to reverse that or do this solar geoengineering thing. That's kind of it. And the active biosphere is just, at some level, along for the ride.
Great, thank you.
Okay, it looks like that's it. It looks like there's no more questions. So let's have a round of applause and thank our speakers. We have another quick 10-minute break, and then we'll be back for our final panel session. Thank you.